So in the earlier video, which hopefully you have watched by this point, goes into the reality that yes, climate is changing. We looked at several maps, we looked at several graphs, and broke down the panel that does all the research and provides the public with the information about this. But let's go down and look at the why this is happening. First, it's a good reminder of what the atmosphere looks like. We looked at a graph like this before where we're looking at what the atmosphere, how it's extended. It's a very, very thin layer around our planet in comparison to how big the planet is, yeah? But it's really important to note here that climate change is a tropospheric phenomenon. So the temperatures of our oceans and lower levels of the Earth's atmosphere are increasing. I think I actually saw an article earlier, maybe even earlier today, that was talking about how there's other changes that we're seeing in the stratosphere and mesosphere where it's actually cooling up there. But we down yonder are warming, as we saw in the earlier video. But it's good to remember our planet as a whole and the physics behind our planet and where we get our energy from. Where do we get our energy from? I think it's the sun. That's probably a good reminder, yes? And the sun energy comes at us in the form of electromagnetic waves. And there's just some terms here to remind ourselves of the anatomy of a wave. So wavelength refers to how long the wave is from the top of one wave to the top of the next wave, right? So that would be our wavelength. This little term here is lambda. And then we receive the waves in a frequency, and meaning how fast these waves have been received. And we have a low energy, long wavelength, and low frequency, as opposed to a higher energy, shorter wavelength, and a higher frequency. So you can compare these two waves here. I only see 3 on the top, and I see 1, 2, 3, 4, 5, 6 here at the bottom. So more waves, shorter wavelength, and would also be considered a higher energy. Warmer objects, again, have a higher wavelength and emit more radiation. If you've ever done anything like been in an infrared sauna or done any sort of heat therapy, those are higher wavelengths waves. This figure here is looking at the difference between the sun and the Earth's emitted energy. It's really important to pay attention to the units that are used here. 10 to the 8th power versus not 10 to the 8th power. So this would be like, 20 million watts per meter squared per micrometer, as opposed to the Earth, which emits at just below 60 watts per meter squared per micron. So this is just to really say that the sun is a heck of a lot hotter than the Earth, which makes sense, right? And we can break down these two terms of waves as being short wave or long wave. So the sun emits short wave radiation and the Earth emits long wave radiation. So those are terms that you will likely hear often. But what happens to all of this radiation as it comes through our atmosphere? There's 4 main things that happen to incoming solar radiation. The first would be transmission. So it doesn't stop, doesn't pay $200, it just goes through the atmosphere. So that's, it can be short and long wave, and it's not interacting with any of the other gases or particulates in the atmosphere. There's also absorption. So that's when energy is then absorbed by an object, which actually depends on the wavelength of the radiation and how well an object can absorb something. Next, it can be reflected. So reflection is when the light or radiation bounces back from an object at the same angle and intensity that it was received. So think of something like a mirror. So same angle, same intensity. Lastly, we have scattering. So this is when radiation is forced to deviate from a straight trajectory. You may be familiar with scattering because if you've ever seen a sunrise or a sunset and have wondered to yourself, why is that a very pretty orange, pink, and yellow sort of color? That's because the sunlight is being scattered. It's going through more atmosphere and it's being scattered a bit more, which is creating those lovely sunset, sunrise colors. But why does all of this matter? Well, in terms of climate change and keeping our atmosphere nice and warm, maybe you've heard of this theory of the greenhouse effect. So all of that put together, thank goodness we have the atmosphere that we do, because it creates a lovely blanket that traps some of this outgoing long wave radiation. If we did not have our atmosphere and the composition of the atmosphere that it is today, then we would be very, very, very chilly. The larger the concentration of the atmosphere has of a specific gas, the greater the likelihood of that gas trapping heat. A common buzzword for greenhouse gases include carbon dioxide, methane, and water vapor. Water vapor might be a little bit surprising to hear that is a greenhouse gas, but it is indeed that. So a way that I like to, an anomaly, or excuse me, an analogy that I like to use for the greenhouse effect and greenhouse gases are thinking of like sweatshirts or hoodies that you wear. You probably have at least one or two hoodies or jackets, right? I mean, especially if you're living in San Francisco, gotta have a jacket. Think of these various gases as a different thickness of hoodie or jacket. So maybe you have one light hoodie for when it's not super cold, and maybe you have a thicker jacket for when it is really cold. So you could think of carbon dioxide as being, like an average hoodie, methane being like, I don't know, like a North Face super poofy jacket that really, really traps your outgoing energy, your outgoing heat extremely efficiently. So again, going back to this idea that if we had no atmosphere, then we would be emitting a ton of infrared radiation, but nothing would be able to trap that outgoing radiation. And that's exactly what our atmosphere does. So this is looking at the absorption and re-emission of infrared radiation by water vapor in particular. So yay, we have an atmosphere. That's awesome. And again, those various gases can absorb outgoing radiation more efficiently than others. So if we were to look at a lovely little graph of some of the various gases that are also responsible, not just carbon dioxide, that's the big one, yeah, but methane and nitrous oxide are also shown to increase the greenhouse effect. Methane, you can kind of think of it this way, that methane, one molecule of methane is equal to 23 molecules of carbon dioxide. So it is very, very efficient at trapping outgoing long-wave radiation. And there is a massive concern because there's a lot of methane that is trapped in the permafrost of some of the Siberian tundra regions that will then seep out when the permafrost melts. Not going to be a fun thing, right? Because again, if it's more efficient at trapping things, then it's going to trap things even better, right? And water vapor and CFCs and tropospheric ozone are also other gases that are of concern. Water vapor, interestingly enough, maybe you've not heard of it as being a greenhouse gas, but if you've ever been to a humid area, like maybe the South or, like New Orleans or Miami, places like that are super, super humid, it makes it feel like it's so much freaking hotter because it's trapping that heat really, really efficiently. And there's a way, maybe you've heard of, that we have been measuring atmospheric carbon dioxide since the late 1950s. And this is called a Keeling curve. So you can see here that there's a very clear upward trend, right? This is the Keeling curve. These are measured out of Mauna Loa Observatory, which is in Hawaii. And I recommend and encourage going through this website. You can just Google Keeling curve and it'll take you to the Scripps Institute of Oceanography, and you can check out the full record. You can look at 1 week, 1 month, 6 months, up to a year, and then the past 800,000 years, etc. Today, I got this screenshot this morning. We are at 419.4 parts per million, which is the highest. Well, I think we exceeded 420, I think a week or two ago. What you can also observe in this graph, which is pretty interesting, are these little itty bitty oscillations that are also occurring. Take a moment and consider why that is. The reason that we see these little oscillations is due to seasons, right? The northern hemisphere has a lot of land mass, a lot of forests, and in the summertime, when these forests are in full, I don't want to say bloom because that's not the right word, but in full force, they are doing their tree things, their plant things, and intaking carbon dioxide, right? They're doing the photosynthesis and releasing oxygen for us to help breathe. So when we're in the summertime, we're taking in more CO2, which causes a global decrease in CO2. But then once we get into our fall and winter months, then they're not doing that as well. So that's when we see that uptick. So that's kind of the why and how climate has been changing, or more so the why, not so much the how, I suppose. But that's kind of the driver of how climate has been changing. And in our next video, I will go through some of the climate system in and of itself and this idea of feedback loops, as well as going into the impacts and effects of climate change.